Today, we're going to be talking about how we can multiply vectors. There's many different ways. Specifically, we're going to be looking at dot product, also referred to as scalar product. I'm going to go through the mathematical procedure, and then I'm going to talk about what it means physically and give us some examples of this used in physics. So, let's first consider two 3D vectors. We have two vectors, vector A, 1 x hat plus 0 y hat plus 2 z hat, and vector B, 3 x hat plus 4 y hat plus 5 z hat. So now let's look at what happens when I do a dot product A dot B. The procedure for dot product is to take the like components, so the components in the same direction, and multiply those corresponding magnitudes together. So what this looks like is the x component, 1 times 3, plus the y components, 0 times 4, plus the z components, 2 times 5. So if I do the math here, we just get 3 plus 0 plus 10, which just is equal to 13. I might also add, if you guys are curious, if I was to take b dot a and multiply the components, it would look like 3 times 1 plus 4 times 0 plus 5 times 2. And what do you know? It's the same thing. So we can say that a dot b equals b dot a. And hence the name of this being a scalar product is because we start with two vectors and we end with just a scalar. There's no more vector or direction here. We just get a magnitude. If we want to get a bit more technical when we get to our dot products, what's really happened is when we took our vectors, we were actually distributing the components together. And the definition of a dot product is that parallel unit vectors, their dot product is 1, and perpendicular unit vectors have a dot product of 0. So what that means is x dot x is just equal to 1, which is the same as y dot y and z hat dot z hat. Now, if I was to look at the perpendicular vectors, what happens is dot product of perpendicular vectors is equal to 0. So x hat dot y hat is 0, and x dot z hat and y hat dot z hat is also 0. Why do we care about dot product? Well, one way we could think about a dot product is it lets us know how parallel different vectors are to each other. So let's consider an example in 2 dimensions. We have our y-axis and our x-axis, and we're going to take 2 example vectors. I know mathematicians like to use u and v. I'm going to use u and w. Just going to define some vector u equal to 2 in the x direction. Now, this is not a precision vector, so it does not need a start at the origin. Now I'm going to define a vector w that's always going to have a magnitude of 1. My first w is just going to be purely in the x direction. So if we were to do the dot product of u and w1, we get this is just equal to 2. Now, what I'm going to do is going to rotate out w. I'm going to rotate w such that we get w2 that's going to be 45 degrees above u. So I'm just raising this vector up. So it's no longer purely x, it's now in x and y. Because it's at 45-degree angle, the x component and the y components are equal. So now, let's see what the dot product is. So we're going to multiply the x components together. And now we need to add the y components. U is just at the x direction. So there is a y here. It's just equal to 0. So when we take the dot product of u and w2, we get 2 times square root of 2 over 2 plus 0. The y component cancel out. Root 2 is smaller then 2. Let's see what happens if we make W2 perpendicular. So we're going to consider W3 as perpendicular to U, so it's just going to go straight up in Y. W3 is now just in the Y direction. So if we take our dot product, what this becomes, well, W3 has nothing in the X direction, so we just get a 0 from W3. And then U has nothing in the Y direction, so we get 0 from the Y components. As we were rotating our vector, W, when it was parallel, we had the maximum possible dot product. But as we became less and less parallel and more perpendicular, we eventually go to a dot product of 0. If the dot product of any two vectors is ever equal to 0, that means they're perpendicular or orthogonal to each other. When they're parallel, that maximizes the dot product. This leads us to a new definition of dot product. We were considering some angle here, whether it was 0 degrees, 45 degrees, or 90 degrees. We could consider any angle we want, and it turns out that we can write that the dot product of any two vectors, A dot B, is going to be equal to the magnitudes. Consider whether they were parallel to each other, it's just the magnitude, and we're going to multiply by some function, particularly a trig function. What trig function should we use? In this example, when U and W were parallel to each other, theta is equal to 0. And U dot W1 was just equal to the magnitude of U times the magnitude of W1. And there's going to be some trig function here to scale it. Trig of 0 degrees. Well, we know this is equal to 2. The magnitude of U is always 2. The magnitude of W is always 1. So we want the trig function of 0 to be equal to 1. And when we had the opposite case, where we were perpendicular to each other, when we were looking at W3, this is going to be equal to the magnitude of U, the magnitude of W1, which is still 1, times the trig function of 90 degrees. Now, wherever in physics you see stuff decreasing or increasing based on angle, you should be thinking there's either a cosine or sine relation, and now you just need to use a limiting method to determine which one we want to use. Well, this has to be equal to 0, so we know the trig of 90 degrees is 0. Trig of 0 degrees is 1. We choose cosine. Cosine of 0 is equal to 1. Cosine of 90 degrees is equal to 0. And that's the second definition of dot product. We could actually also see another representation of why this is cosine if we make a graph of the dot product versus the angle between our vectors. Y-axis is just going to be the value of U dot Wi versus theta. When theta was equal to 0, that was just equal to U dot W1, which was 2. When we look at U dot W2, at 45 degrees we go to root 2. The square root of 2 is about 1.4. And now our final dot product. When theta was equal to 9 degrees, we were perpendicular to each other. We have value of 0. Now what's going to keep happening is, if I was to rotate W so that W was now anti-parallel, so instead of them both pointing in the same direction, I have a new W, the opposite direction. This W will have a minus sign, And instead of our dot product being equal to 2, we will have a dot product of minus 2, which means still anti-aligned. If we keep repeating this for all possible angles, we will get a graph that looks like this, which looks like a cosine graph multiplied by an amplitude of 2. Where would we have seen dot product in physics already? We'll all see dot product used a lot when we get to integrals and more derivatives here, but a basic example you should have seen earlier in your physics career is walk. So walk is defined as a force, where force is a vector dotted with the displacement. What this means for walk, you may remember, we take our object and put it on the ground. Right now, there's going to be two forces acting on it, the normal force and the gravitational force. Now let's take my elephant here, and the elephant is going to apply some external force to push the car. So what happened was we had displacement as the elephant applied the force to our car. We had applied force from the elephant, gravitational force, and the normal force. So if we were to look at the walk done here, the normal force and the gravitational force are both perpendicular to our displacement. Did either of those forces do any walk? No, because perpendicular forces never do any walk. But the applied force did do walk. So walk could be force applied from our elephant on our car times the displacement. But that only works if the force of the elephant and the displacement were in the same direction. However, if they were not the same direction, if our elephant was pushing at an angle, but our car still only moved in a straight line. The car gets pushed by the elephant, which is pushing like this. It's pushing up at an angle, but it still only moves straight. The walk is not just the magnitude of the force anymore, it's just the parallel component. So if we were to look at our force applied vector and our displacement vector, we will only want to resolve the component of the applied force that's parallel to our displacement. We will only want the parallel component. Well, the parallel component would just be equal to the magnitude, FA, times the cosine of the angle between them. So our walk here would be equal to force applied parallel displacement. Well, force applied parallel is just force applied cosine of theta displacement. Walk is equal to the magnitude of FA, magnitude of the cosine of theta, which as we've seen is just the dot product of the applied force dotted with the displacement vector. That's where you see dot product in physics.